Okay, good morning. So, in the previous lecture, we discussed about the flow regimes, and specifically we talked about the subsonic flow, transonic flow, supersonic flow, and hypersonic flow. Apart from that, we have also studied about the fundamental equations for the ideal gas, and there we have seen that the very first type of gas we call as nothing but calorically perfect gas. So calorically perfect gas is something which is nothing but ideal gas having what? Having constant Cp and Cv. So this is something which is valid up to a temperature of nearly equal to 1000 Kelvin. Then we saw that if we go beyond 1000 Kelvin, then actually what happens at temperature greater than equal to 1000 Kelvin, we see that uh, in case of Cp and Cv, dependence of temperature comes. Okay, so here Cp and Cv are functions of temperature. So when these are functions of temperature corresponding to this, we call this gas as nothing but thermally perfect gas. So gas is perfect, but still it is not calorically perfect because now Cp and Cv are showing dependence on temperature. Then we have if our temperature is greater than equal to 2500 Kelvin, then actually real gas behaviors become important. Why? Because uh, we see that above this temperature ionization of the oxygen molecule takes place. Okay, and even at temperature greater than equal to 4000 Kelvin, we see ionization of even the nitrogen molecule also takes place. Okay, so under these conditions gases will go nothing but the chemical reactions, so that's why we have to consider the real gas effects over here. Okay, now let's try to see some of the revisions to the concepts of fundamental thermodynamics. Okay, so very first thing we will start with the term energy, because ultimately what we are having, the involvement of energy in the high speed flows, and then that energy will be having different effects actually. Okay, so first let's talk about the internal energy and enthalpy. Okay, so these are very important quantities in our fundamental thermodynamics. So can you tell me what is internal energy? Any definition for internal energy? See, whenever we have any object, that object can have two different types of states. One is called as its physical state, second one is called as its thermodynamic state. Okay, so there are two states. One is thermodynamic state and another can be its physical state. Okay, for example, if you have a glass of water, okay, so if a glass of water is at 1 atmospheric pressure and 25 degrees Celsius, and now say it is in this room, so this room is at the ground level. Okay, now you go to first floor, one room above. Now the same glass of water having 1 atmospheric pressure and say 25 degrees Celsius temperature is actually having some elevation with reference to the ground. So I can say that physical state of that particular glass of water is now different, because that is now having different elevation, whereas its thermodynamic state is the same. So it is acting like a liquid only. It is having pressure of 1 atmospheric, temperature of 25 degrees Celsius, and even if you find its other thermodynamic properties which depends upon its thermodynamic state, for example internal energy, enthalpy, entropy, etc., will also be the same. Okay, then same glass of water on the first floor, but now the person who is carrying that glass of water, he is also moving at say some velocity. So now you can see in physical state of the system one more object has come, and that object is nothing but the movement of the system. So that glass of water, you can consider water within the glass boundaries, that you can consider as your system. So initially the system was on ground floor and that was static. Okay, so now when you went to the first floor, then its elevation has increased. So it means the system has gained the potential energy. Okay, it will be having certain mass. When you have raised it through certain height, then it has gained potential energy. When a person started walking, then it has gained some velocity also, some kinetic energy also. So it means that you can say with the physical state of the system, whatever energies are associated, these are nothing but the kinetic energy and potential energy. And kinetic energy, we know the fundamental formulation as half mv square. Okay, and this potential energy is mg into, say, z, where z is the elevation. Okay, but one important point is that even when the glass was on ground floor and stationary, and when a person is walking, then also the thermodynamic state of the glass is actually remaining the same. So if its thermodynamic state is remaining same, so thermodynamic properties are actually not changing. So first point is that internal energy and enthalpy are nothing but the thermodynamic properties of the system. So being a thermodynamic properties of the system, these depend upon thermodynamic state of the system. Okay, so say if you change, you might have seen in basic thermodynamics course, we are having properties of air, properties of steam. So when we go through the steam tables, we find that if you change pressure or temperature, corresponding representation on PV or TS diagram changes, and the corresponding values of internal energy and enthalpy also changes. Okay, so it means that internal energy and enthalpy, crudely we can say that these are something which are associated with the thermodynamic state of the system. Okay, so if thermodynamic state is changing, then these will change. But the point is how and in what form these energies are actually saved. That is important to know. Okay, so can you tell me how internal energy is stored in a substance, say in a glass of water, what I talked about? Okay, so that is correct. One is molecular movement, but molecular movement can have variety of things. Okay, so let's try to see first the constituents of internal energy. Okay, so if you talk about constituents of internal energy is given by a symbol U. So capital U will be internal energy and small u will be specific internal energy per unit mass. So specific properties, any property on per unit mass is known as specific property, and it is of intrinsic nature. Okay, so U will be equal to U intermolecule plus U translation plus U intramolecule. So now can you tell me what is the difference? U intermolecule represents the interactions between the molecules. U translation is related to the translational kinetic energies of the molecules, and U intramolecule is related to the within a molecule what are the movements, and because of these movements what energies are actually what energies it is constituting. Okay, so for example, if I have, say, a gas in a container, so say I have number of gas molecules over here. Okay, so what will happen, say this gas molecule is having some velocity in this direction, this is having some velocity in this direction, so randomly these will be having some motions. So these all molecular translation from one location to other location. Okay, so we know that in case of liquids and solids, the bonds are actually in case of liquids and gases, the bonds are weak and molecules do not stay at fixed locations. So these keeps on moving here and there. Okay, so in case of gases, even molecules are more loosely packed and they will be having significant translation. Okay, translational motion. So this is something which is contributed because of the U translation. So if you take the sum of all the kinetic energies of the molecules, okay, so that is something that is forming this constituent U translational. So that is also contributing to the internal energy, but some fraction of internal energy. Okay. Then comes U intermolecule. Now we know that when two molecules are actually far apart, then these will not be having any interactions. Once these molecules comes at say sufficient distance close to each other, then we will be having some attraction forces between the molecules. So this molecule will try to attract this molecule. Okay. If you go at more closer distance, then what will be happening? Now molecules will be so close to each other that these will try to repel each other. Okay. So this type of intermolecular forces actually accounts for some portion of the internal energy. So that is accounted over here. Is this point clear? Intermolecules means when two molecules are coming at sufficient distance close to each other, initially they will show some attraction energies. Okay, so it means that if you have to bring these molecules apart from this distance, you have to spend some amount of energy because these are having certain attractions. So that energy is actually constituted in the form of U internal molecule. Similarly, when two molecules are very close to each other, they will, in order to hold these molecules at that location, you have to supply some energy. Otherwise, they will have tendency to move away from each other. Okay, so that portion of actually internal energy is coming into this intermolecule. Then comes the next portion, which is very, very important, that is U intramolecule. Now, in case of U intramolecule, we can have further many constituents. So, one of the constituent is because of the rotation of a molecule. Another constituent is because of vibration of atoms in a molecule. Then there can be rotation, vibration. Within an atom, what happens? Within an atom, we are having some protons and neutrons binded together. So if an atom is being disturbed, for example, in case of nuclear fission reactions, what happens? Actually, the nucleus of the atom is being splitted, okay, and in case of nuclear fission reactions, you will be finding significant amount of energy releases. Okay, so that is something which I am actually trying to put in U atom. Then I have some energy in the form of U potential. So within a molecule also there exists potential. For example, you have carbon dioxide molecule. So what will be having? In between carbon and oxygen, there will be some bond. Okay. So if you have to remove the oxygen atom from a carbon atom, you have to spend some amount of energy to break that bond. So that energy is actually stored in the form of potential. Okay. So I can say that, say I have one molecule, say O2 molecule. So O2 molecule will be something like this. Now say this is my coordinate system X, Y and say this is Z. Now this O2 molecule can have different type of rotational motions. One rotational motion can be along this axis. So it is rotating something like this. Okay, like revolving a pen. Then another motion can be this whole can rotate in this direction. So it can rotate about this Z axis, whole molecule. Then it can have one motion about Y axis. So it means it can have large number of rotational motions. So the rotational motion which I have shown you initially, the rolling one, in case of rolling rotational motion, what is happening? The rotation is actually coinciding with the center of mass. So in this case, we will not be gaining any kinetic energy. But the motion which I have shown in this direction, this particular motion about Z axis, here its center of mass and the center of rotation will be having some difference, okay, in distance. So in this direction, it will possess some rotational kinetic energy. Is this point clear? So it means this type of rotations of the molecules are contributing to U rotation within a molecule. Another is, I told you that if I have say two oxygen atoms bounded together, these oxygen atoms at their location will have some vibrational motion. Okay, molecules does not stay, atoms in a molecule does not stay at fixed location. They will be having certain vibrations. So because of these vibrations, actually whatever energies are contributed, these we are calling as nothing but the U vibrational energies. Okay, then we know that if say this is the nucleus of an atom, around this electrons are orbiting. Okay, we will be having some or motion of the electrons, and electrons are also having certain amount of mass. So it means these are also contributing certain amount of energy. Then similarly, any electron or proton, they are also having some spin kind of motion. So along their axis also they keep on rotating while they orbit around the nucleus. Okay, so here also they will be having certain, say, spinning kind of motion. So these electronic and proton motions will also contribute to certain amount of energy. Then another thing is, so this I can say that energies within an atom. Similarly, energies within an atom can be because of you have all positively charged proton at the center of a nucleus and some neutrally charged neutrons, and these are binded together in the nucleus of an atom, and outside that we are finding electrons are revolving. So if this nucleus of the atom is broken, then also it will be releasing significant amount of energy. So that is actually energy stored in the form of its chemical energy. Okay, so all these are nothing but the constituents of U atom. Sorry, not chemical energy. Energy is stored in the form of its nuclear energy. Okay, so this is something which is the constituent U atom. Then another thing can be, like I told you, say in case of CO2 molecule, this is my C, this is one O, this is another O. So if you break this bond, you have to once again put certain amount of energy. Okay, so this energy is stored in the form of potential of a molecule. Okay, so once the breakage of bonds takes place, then depending upon the nature of the molecule, it can undergo some chemical reactions, and while it is going through the chemical reactions, then depending upon the type of the reaction, whether you have to supply energy to break the bond, or whether once you have broken the bond it is releasing significant amount of energy, we can have endothermic or exothermic reactions. Okay, is this point clear? So all these are nothing but the constituents of internal energy. Now if you change the thermodynamic state of the system, say you are at 1 atmospheric pressure 25 degrees Celsius, if you increase the temperature to say 90 degrees Celsius, what will happen? All these molecular motions will change. So when these molecular motions are changing, actually under that scenario we will be having changes in internal energy and other dependent properties of the material. Okay, so it means that internal energy is something which is inherently associated with an quantity of matter due to its thermodynamic state, and ultimately at molecular level it is contributed because of the large number of molecular movements. Okay, another important point is, so this is the categorization of constituents of internal energy on the basis of molecular motions. Similarly, each of these molecular motions give rise to different types of energies. So for example, internal energy of a molecule can also be divided into 4 categories. One is sensible energy, then latent energy, then chemical energy, and then nuclear energy. Okay, so when you are upon increasing the temperature or decreasing that temperature, it means upon changing the thermodynamic state, only the molecular translational motions are changing and there is not much change in the molecular distances, then we say that sensible energy is actually changing. For example, if you are within the liquid state, okay, where molecular distances are not changing much apart, but upon increasing the temperature of the liquid, the velocities, translational velocities of the molecules are actually increasing. Okay, so it means that we are actually changing nothing but the sensible energy. So sensible energy you can relate directly to the translational motion of the molecules. Whenever you are giving energy, say you have reached at 1 atmospheric pressure and 100 degrees Celsius, so you reached the saturation limit. After that point, if you add the energy, then what will happen? Molecular distances will increase. It means you are breaking the potential of the molecules. So you can say that intermolecule potential is coming over here, because within a molecule changes are not taking place. In liquid state below 100 degrees Celsius also, liquid water was existing as H2O molecule, and in the steam phase also it is existing as H2O molecule. So it means you are not breaking the molecular structure. So intramolecular things are remaining the same. Only thing you are changing is intermolecular thing. When you are going to the chemical energy, then what you are doing? You are breaking the bonds. So within a molecule, if bonds are broken and new bonds are formed, so then you will be having actually, so it means one reactant molecule is actually breaking and it is reacting with some other species and forming the new molecule. So then we will be having change of chemical energy, like in case of chemical reactions. Okay, for example, certain chemical reactions are endothermic, where we have to supply the energy. Some chemical reactions are exothermic, where internal energy of a molecule is released in the form of heat. Okay, if you are having an exothermic reaction, for example, methanol molecule, gasoline molecule, diesel molecule, whatever we use as the common fuel in our automobile vehicles. Okay, these are storing energy in a fuel tank in the form of chemical energy, and once these react with oxygen, the bonds are broken and that internal energy is released in the form of heat, and that heat, with the help of certain mechanism, is used to drive the car. Okay, similarly, in case of nuclear reactor, what happens? Like in nuclear fission reaction, the whole atom, core of the atom, actually nucleus, is getting split, and that is actually having energy stored in the form of binding energy at the nucleus. When that energy releases, actually that also changes the internal energy of the system. So what we will be doing in this subject, whenever we will be referring to the internal energy, we will be only talking about the first two constituents. If later on sometimes we discuss on hypersonic flows, then we may enter into this domain. However, nuclear domain we will not be disturbing, because we will not be having any system where actually whole atom is actually changing. Okay, even when you do the study of your fundamental thermodynamics, then also you will be finding that only these two constituents we consider, unless or until chemical thermodynamics we are considering, chemical reactions are involved. Okay, so this is all about internal energy. Then we have enthalpy. Enthalpy, we say that internal energy plus flow work. So this represents the additional flow work potential of a system, and when that is added to the internal energy, then we call the property as nothing but our enthalpy. Okay, now one important point is I have told you that internal energy and entropy are the properties which are linked to thermodynamic state of the system. So in our basic thermodynamics course, from the state postulates, we know that if we have to define any property, then how many number of independent intensive properties are needed? If you have to locate a state of system on property table, how many properties are needed? Say if you have to find out internal energy and enthalpy of air on a property table, and you are considering air to be an ideal gas. For ideal gas, okay, for water vapor, do you remember the superheated steam tables? So if you have to locate a state in superheated steam tables, then how many properties are needed? Two properties. Basic thermodynamics. Okay. And for an ideal gas, single property. When you refer to the property table, you only find if you are considering the air as an ideal gas, it comes only as a sole function of temperature. All of you, please revisit your basic concepts. This is very, very important and very fundamental thing. You should be able to answer. Okay. So what I am saying is, as per the state postulates, if you have a simple compressible substance, for a simple compressible substance to designate its state, two independent intensive properties are required. What is required? Two independent intensive properties. What is the meaning of independent? Don't depend on each other. Can I use temperature and pressure as two independent properties when my substance is in the saturated state? My question is, if I have, say, saturated state, can I use pressure and temperature as independent? No. Why? Because at saturation state, pressure and temperature are dependent. For example, at 1 atmospheric pressure, the saturation state of water is at 100 degrees Celsius. But if you go to 2 atmospheric pressure, then saturation state of water will be slightly higher temperature. So at saturation state, particularly at saturation state, pressure and temperature are dependent on each other. If you go away from the saturated regime, then pressure and temperature becomes independent. There you can use, for example, in superheated region or in the subcooled region. Okay. So from the state postulates, it is very clear that we require two independent intensive properties. Okay. So it means that if I have to determine the internal energy, I have to take functional dependence of any two intensive properties. So say I can take it is as function of temperature comma specific volume. Similarly, if you have to define enthalpy, any property, because if you know the two independent intensive properties, then you can determine all other properties from the thermodynamic relations or from the property tables, which are actually basically driven from the thermodynamic relations. Okay. So H will also be function of, say, I have considered temperature and pressure. So it is a usual practice. So right now I am only talking about the gaseous phase. So I am not considering the saturated regime. That's why I can consider temperature and pressure to be the independent parameters. Okay. So now the point is, when my internal energy I am writing as function of temperature and specific volume, so it can be function of any other parameter also. Okay, but I have chosen temperature and specific volume because this is the more appropriate form for majority of the systems. Okay, so you can, in place of specific volume, you can take pressure, you can take entropy, enthalpy, other property also, but these should be independent. But temperature and specific volumes are actually more convenient for defining the functional form of internal energy. Similarly, for enthalpy, temperature and pressure are the convenient form. Okay, so this type of definition is applicable for any simple compressible substance. However, if you further refine this definition, particularly for an ideal gas or an thermally perfect gas, then you will be finding that their internal energy and enthalpy becomes sole function of temperature. Okay, so it means in the gaseous phase you can write U as sole function of temperature and H also as sole function of temperature. Remember one thing, when for an ideal gas I am saying internal energy is function of temperature, enthalpy is function of temperature, don't generalize this definition that other properties such as entropy will also be sole function of its temperature. So whenever later on we will be defining the entropy for a gaseous substance, we will be seeing over there that entropy is not a sole function of temperature. Okay, so for an ideal gas only the internal energy and enthalpy are the sole functions of temperatures. Okay, is this one clear? Now after this we have very important two more properties which are called as specific heats, and these specific heats are actually obtained at either at specific heat at constant pressure or specific heat at constant volume. So the definition of specific heat is, yes, so energy required to raise the temperature of 1 kg of a substance by 1 degree Celsius. Okay, so say uh, and that too, this is the general definition of the specific heat. Whenever you will be supplying this energy, you can supply this energy either at constant volume of that substance or at constant pressure condition of that substance. So depending upon the condition, whether constant volume or constant pressure, the amount of energy supplied will be different. So that's why we then further categorize these as two different values. Okay, so now in general form I can say that I have unit mass 1 by m, and say del Q is the amount of energy supplied, and unit change in temperature is del T, and this is done at nothing but the constant pressure condition. Whenever I will be writing the definition of CV, then I will be doing 1 by m del Q by del T, and that is particularly at constant V. Okay. Now this 1 by m, if I take inside, then I can write this capital Q as Q by m small q. Okay, so small q is say capital Q by m. Okay, so then my Cp will become del small q by del T at constant pressure, and Cv will become del small q by del T at constant volume. Okay, now if I take a quantity of any gas, okay, so this is the quantity of gas. If I heat it, once I heat it, what will be happening? If I heat it at constant volume condition, okay, so if I am heating it at constant volume condition, then what will happen? I have to apply over here first law of thermodynamics. So say I have added delta Q amount of heat minus delta W will be equal to D into E, where E is change in energy of the system. Okay, so E includes changes in internal energy plus changes in kinetic energy and potential energy. As the system is stationary, so its kinetic and potential energies will be 0. So I can simply write it as equal to du. And if the boundary of the system is fixed, so if boundary of the system is fixed, it is, we are doing it as constant volume condition, then this delta W will be 0, because in case of a closed system, delta W is nothing but the boundary work which is given by symbol PdV. Okay, so if PdV is 0, then my delta Q will become equal to du. So let me write this also small q actually. Okay, so this will become nothing but du. So it means that I can write this definition as del U by del T at constant volume. Okay, similarly if you do at constant pressure, then what will happen? If you are heating at constant pressure, if you are maintaining pressure constant, then upon adding the heat, so that pressure of gas molecule should not increase, you have to increase its volume. So there will be changes in volume also. So if there I have to write the first law of thermodynamics, then I can write del Q minus del W will be P into dV change in volume, say small volume, I am writing in specific form, so specific volume, that will be equal to du. So del Q will become du plus PdV. What is du plus PdV? We have just now seen H is equal to U plus PV. So that will become nothing but our, okay. So here then I can write this as del H by del T at constant pressure. Now just now I told you that for uh, ideal gas, dependence of other properties does not come on enthalpy and internal energy. So it means I can omit this pressure and volume over here. So I can simply write that my, now dependence is on only single parameter. So I can write dH is equal to Cp into dt and du is equal to Cv into dt. Okay, so this is something which I can write for a thermally perfect gas. If you impose the condition of calorifically perfect gas, calorically perfect gas, if you take a calorically perfect gas, then Cp and Cv are constant. If Cp and Cv are constant, then you can simply write these, you can take constant. Okay, and we know that H is equal to U plus PV. Okay, dH will be equal to du PdV plus VdP. Okay, so this we will be getting over here. What you can write dH, this you can write CVDT. Okay, let me take it from the other form. So what I will do, first I will take the first law of thermodynamics. Okay, so let me derive property relations from the first law of thermodynamics. So first law of thermodynamics for a closed system is nothing but del Q minus del W is equal to du. So this is first law of thermodynamics for a closed system. And if you have to write this law, if you have to write this law in the which form? In specific form, then you will be writing it as del Q minus del W equal to d into small u. Okay. Remember one thing, whenever we are applying first law of thermodynamics for a system, any heat which is going into the system is considered as positive. Any heat which is going out of the system is considered negative. Work done by the system is, and work done into the system is negative. So it means this delta W, whenever you will be writing, this will be W net work done is W out minus W in. So if you have W out, you have to keep its positive sign. If you have W in, then you have to supply one more negative sign over here. Okay. So now this is the first law of thermodynamics for a closed system. And remember one thing, in this delta W whatever we are having, that is nothing but a boundary work. So this boundary work will only come into picture when you are having the displacement of the boundary. Okay, so unless or until you are having displacement of boundary, you cannot see any work in case of a closed system. Okay, so it will be only associated with the changes in boundary of the system. Likewise, the first law of thermodynamics, we also have second law of thermodynamics. So first you just tell me why there is need for second law of thermodynamics. What is the need? Okay, so first thing is quality of energy. But what do you mean by quality?
It is basically how much work can we extract from that energy.
Okay, so say tendency to extract useful work you are saying. Okay, anything else? The very important point is whenever we study the first law of thermodynamics,
Direction.
we see the only conservation of energy. Okay, so we are not concerned about the direction in which the process is actually happening. Okay, if process happens say from state 1 to 2, and if we say that any process is happening from state 2 to 1, say a stream of water is flowing from lower position to upper position, it means it is rising through an elevation. So that is also something which is not incorrect as per the conservation of energy principle. Okay, so if a mass is actually, there will be some changes in energy, and that change in energy associated with the system will follow the energy conservation principle. Okay, so it means that how spontaneously the feasibility of a process is there, that is actually we cannot determine from the solely from the first law of thermodynamics. So whenever we do study about the second law of thermodynamics, you will be finding that its two important statements are particularly for heat engines and the refrigerating systems, which are known as Kelvin-Planck statement and the Clausius statement. Over here in this subject we will not be dealing with the heat engines and and refrigerating units. Obviously we may deal with some components of say gas turbines, that is also an heat engine, but at component level we will not be dealing in a thermodynamic cycle. Okay, so we are not concerned about these two statements, but second law of thermodynamics gives one important property. Okay, and it does not give directly the absolute value of the property, but it gives birth to a property which is called as entropy, and we obtain some formulation for entropy change based on the second law of thermodynamics. Okay, so basically by the origin of this property entropy, we come to know the direction in which a process can occur. Okay, so later on I will explain that to you. So first, whenever we are going through the second law of thermodynamics and particularly to the concept of entropy, it is having one important proposition which is called as Clausius inequality. Okay, so I am just giving you the review, you have to go deeper into these subject concepts. Okay, so in case of Clausius inequality, we know that cyclic integral of del q by t has to be less than equal to 0, and if we further break this, we know that cyclic integral of del q by t is equal to 0 for reversible cycle, and it is less than 0 for an irreversible cycle. So up to this we have we know actually. Okay, now we know that for a cyclic process, initial and final states of the process are same. So if initial and final states are same, then it means the changes in property for the complete cycle will be equal to 0. So over here this cyclic integral of del q by t is becoming equal to 0. As it is becoming equal to 0, it means it has to be some property of the system. Okay, is this point clear what I am saying? For a cyclic process, any quantity is equal to 0 is nothing but a property of a system, because initial and final state are same. If initial and final state are same, the property values at initial and final states will be same, and change in property will be 0. So if anything is becoming equal to 0, I can designate that thing nothing but as a property of the system. So that change we designate as nothing but our ds. But remember one thing, over here we have defined this one nothing but for a reversible cycle. Okay, so this ds equal to 0, it is showing that S is a property of a system. Okay, and if S is a property of a system, that particular property should have some name, so we call this property as nothing but the entropy. Okay, we know that entropy, a property of a system, is nothing but a state function. Okay, so you can see that your delta q over here was inexact differential. What is delta q? It's a path function. So delta q is not a direct differential. It is, mathematically I can say, it is a inexact differential. So when I am dividing this delta q by t, this is becoming nothing but a exact differential, because it is becoming property ds. So mathematically, if you multiply an integrand to a mathematically in exact differential, it becomes nothing but a exact differential. So 1 by t is actually that multiplier which is making your inexact differential as exact differential. Okay, so right now what I have done, I have just written this statement ds is equal to del q by t cyclic integral for a reversible process, and that too for nothing but a cyclic process. So likewise, when we extend this statement, we find that ds equal to del q by t is applicable for a process as well, if it is reversible. Okay, so I am not going to explain that, but just for your knowledge, if we recapitulate, so we comes to know that, so all of you please go through any basic thermodynamics book. So if you see ds, you will be finding equal to del q by t equal to 0. This exists even for a reversible process. Okay, once this is existing equal to 0 for a reversible process, then what will happen? For irreversible process, we get plus some delta S generation over here, and this parameter is called as nothing but the entropy generation. Okay, so this is the generalized equation of entropy. So for a reversible process, I can say that del q is nothing but, in a reversible manner, it is nothing but equal to TDS. However, if you are having a reversible process, then always you will be having some sort of entropy generation within the system. So if you are having entropy generation within the system, then the change in entropy during a process will not be solely equal to del q by t. Okay, so now the general statement, you can say that, in general you can say ds is equal to del q by t plus delta S generation, where delta S generation is equal to 0 for, and delta S generation is greater than 0 for irreversible process. Okay. Now see one important point, how this entropy actually helps us in determining the direction of the process. So what I am doing over here, I am giving you just idea of some of the briefly I am writing these equations without going into much their deeper explanation, but some of the ideas which will be very relevant for compressible flows, these I will try to give you the details. Okay, so what I am saying now, say I have a system, and say a system is as large as a steam thermal power plant. So if you have a thermal power plant, somewhere you will be having boiler, somewhere you will be having furnace. Okay, then somewhere you will be having your turbine, then generator, condenser, cooling tower, many systems we will be having. So say this entire thing is nothing but a steam thermal power plant, and this is our system. Okay, so if this is the system, this system can exchange heat and work with its surroundings. Is this one clear? So this is a system. This system can exchange heat and work with its surroundings. So obviously you will be finding, if you go near to a steam thermal power plant, that from the cooling tower a fume is coming. Okay, from the chimney of the thermal power plant some hot gases are coming, which are nothing but the products of combustion, and ultimately these are going and mixing into the surroundings. So if these are going and mixing into the surroundings, these are resulting in nothing but the mass energy exchange with the surroundings. And outside this boundary of the thermal power plant, you are having some electrical connections through which electricity is going out. So electricity means it is nothing but a work. So you are having some electric work interactions also over there. Okay. So if you observe a steam thermal power plant, you will be finding near the plant area, whatever surrounding is there, that surrounding is also actually influenced. Okay, because of the system. So in the immediate area closer to the thermal power plant, you will be finding just above the chimney a black fume is there, then above the cooling tower a white fume is there, where actually water vapors are present. So their humidity level is different. So you can see that the humidity, temperature, chemical affinity of the area which is in immediate vicinity of that power plant, that will be different than the atmospheric area which is at sufficiently far distance from that location. Okay, so our general tendency was in basic thermodynamics that we are concerned only within this boundary, which we call as our system, and outside system everything is nothing but our surroundings. Okay, however, we experience that the immediate portion of the surroundings which is very closer to the system boundary, that is also affected by the system. Okay, so I can say that if this is my surroundings, I can divide surroundings in two portions. One is this immediate portion of the surroundings. This is the immediate portions of the surroundings where gradients of temperature, say del T by del X vector, gradients of concentration, del T by del X vector, etc. can be present. Okay, so this is the reason where gradients of different properties are present. If gradients of different properties are present, then it means in this region also there will be the effect of the system. There will be reactions, there will be heat transfer, there will be different temperature. However, the region outside this green boundary, I can say where all the gradients has vanished and everywhere we have the same temperature. So here also T, here also T, here also T, and this is nothing but equal to the ambient condition T naught. Is this point clear? Similarly, pressure also. So whatever outside surroundings I am having, that surrounding I can divide into two parts. One I can call the immediate surroundings, and another I can call nothing but the environment. Okay, and I can say that if I take this green colored boundary, so this green colored boundary is forming a thermal universe. What is the meaning of thermal universe? The meaning of thermal universe is that any heat energy interactions are taking place. These are taking place within this inner boundary, and as outside this boundary there is no T naught, P naught, etc. Everything is same. So it means outside this boundary the heat interaction is zero, work interaction is, and mass interaction is, outside this boundary nothing is happening. So I can call this inside everything inside this outside boundary as nothing but an isolated system for this particular thing. Okay, and this complete isolated system, which is a combination of what? System and its immediate surroundings, that I am calling as a thermal universe. So this thermal universe is nothing but becoming an isolated system. Now let's go back to our entropy equation. So our entropy equation is ds is equal to del q by T plus delta S generation. Now just now I told you that we have obtained some thermal universe, and for this thermal universe, what is there? For this thermal universe, I can approximate it as nothing but an isolated system. If this is an isolated system, then for this delta Q will be 0. So any change of its entropy will be equal to delta S generation. And obviously within the thermal universe, when practically the processes will be happening, all the practical processes will be nothing but irreversible in nature. There will be certain amount of irreversibility. If all the practical processes are irreversible in nature, then ds generation will be, so it means change in entropy of this universe is greater than equal to 0. So this is something which is called as the principle of increase of entropy, or in other words I can say that for our universe, because if I consider all the things inside our atmosphere as nothing but the different systems, okay, so all the systems are completely encapsulated around our atmospheric boundary, and outside the atmosphere, we, apart from say solar interactions, we are not having any other interactions. So I can consider the universe also to be an isolated system. So they are also within the universe also, every day we are having lot of irreversibilities happening. So I can say entropy of the universe every day is actually increasing. Okay, so in general, if I have a system and its surroundings, ultimately the process will happening in such a way so that the entropy of the universe is actually increasing. Okay, and in all the spontaneous processes we will be having some sort of irreversibility associated. As irreversibility is associated, that's why processes should happen always in the direction of increasing entropy. Okay, so for a spontaneous process to occur, it will be taking place in a direction where its entropy is actually increasing. Is this one clear? Now what we have, we have the first law of thermodynamics, del Q minus del W is equal to du. Okay, and del W for a closed system I can write as PdV, and del Q particularly for a reversible process I can write as T into ds. So if I write, say this is on per unit mass basis, so the d is, s is small, so then I get T into ds minus P into dV is equal to du. So you can see now this first law of thermodynamics completely I have obtained in the form of properties. So T is property, S is property, P, V, everything over here is nothing but a property of the system. So that's why this is called as actually thermodynamic property relation. One important point, being it a property of the system, this should be applicable for any process, reversible or irreversible, because properties does not depend upon the path of the function. However, if you have to use this equation and if you have to integrate this equation to find out delta Q, to find out delta W, then that integration has to be performed only along a reversible path. Okay, because for irreversible path you cannot fully define the exact path. Okay, and there you will be having more generation term also. Okay, so that's why you cannot perform the integration of this one along a irreversible path. Another important point is H is equal to U plus PV. So DH will be equal to so from here du plus pdv I can write as TDS. So DH I can write as TDS plus, or I can write that T into ds minus VdP equal to DH. Sorry, TDS equal to DH minus VdP. So this is another thermodynamic property relation. So this is typically known as Gibbs first relation, the top one. And second one is known as Gibbs second relation. Okay, so what we will be doing whenever we will try to now integrate these equations in order to obtain entropy change for a gaseous substance. Okay, so that part I will take up in the next lecture. If you have any questions that you can ask.